Hi, my name is Glenn Weinreb, and today we're going to talk about climate tipping points and what to do about them. This is part 9 of our climate solution video series. Tipping points are additional sources of global warming that add to the global warming that is already being done by carbon dioxide. North Pole sea ice is an example tipping point. It is 2 meters thick, and when it melts, sunlight is absorbed by water instead of being reflected by ice, and the planet's temperature increases. Thawing permafrost is another example. It releases methane, a greenhouse gas, which also causes the planet's temperature to increase. A recent OECD report identified 17 such tipping points, shown here. This YouTube channel focuses on how to solve climate problems. There are two. One is global warming due to carbon dioxide, and the other is global warming due to tipping points. We break each problem into 5 areas: background material, strategy, policy-making tools, R&D, and large-scale production. Our videos hope to explore all areas of both problems. We're less interested in what is being done and more interested in what could be done if we tackle the climate problem at the lowest cost. We call this doing climate the easy way. Our last video explored policy-making tools for the carbon dioxide problem, whereas this video explores policy-making tools for the tipping point problem. In both cases, these tools do not exist. However, they could be developed. Resolving tipping points probably involves putting material into the atmosphere to reflect more sunlight back into space. This might seem like a bad idea. However, we are already doing this when we burn fossil fuel. The exhaust from burning fuel is often not good for health. Therefore, if we intentionally added material to the atmosphere, we would probably do it far from people. For example, we might target the stratosphere, which is above where airplanes typically fly. To justify the expense, we would need to compare the cost of cooling the planet with the cost of not cooling the planet. Here's an example. This study suggests large-scale planet cooling would cost $18 billion a year. For comparison, the total value of New York City property is $1,300 billion. And this is just one coastal city that would be lost to sea level rise. Climate tipping points can activate each other and are therefore like dominoes. One of the first dominoes is North Pole sea ice. It is expected to melt over the next 15 to 20 years, and this will cause snow and ice on Greenland to melt, which will dump fresh water into the Atlantic Ocean and reduce heat transfer due to loss of ocean currents. Unfortunately, this will cause land suitable for growing corn and wheat worldwide to decrease twofold, according to a recent OECD report. Reputable studies expect all of this to occur before mid-century. We probably cannot fix the tipping point problem by reducing carbon dioxide emissions. This is because the planet is tipping too fast. In other words, to resolve this, we might need to begin large-scale atmospheric intervention 3 to 10 years from now. And we would need to do R&D at the billion-dollar level for several years before that intervention. Our society is faced with this fundamental question. What does it cost to block the first domino in this line of cascading tipping points? To answer that question, we need to develop better instrumentation for monitoring atmospheric reflectivity, develop equipment that injects small amounts of material for purposes of field experiments, and develop equipment that injects large amounts of material for full-scale deployment. 90% of the sun's energy reflects off of ice, whereas the opposite is true with water, which absorbs 90% of the sun's energy. In other words, the Earth becomes warmer when we lose sea ice. The surface area of North Pole sea ice is approximately 5 million square kilometers, and the surface area of the entire planet is approximately 100 times more. Therefore, we need to reflect on the order of 1% of sunlight back into space. People would barely notice. An aerosol is a tiny particle or liquid droplet suspended in a gas. There are natural aerosols, such as fog and volcanic exhaust. And there are man-made aerosols, such as vehicle exhaust. Sunlight typically reflects off of aerosols and back into outer space. Therefore, aerosols are often considered to be negative components of global warming. In other words, sources of global cooling. The atmosphere does offer one piece of good news. A plot of temperature versus altitude shows that it gets colder as we go up. However, this reverses at 20-kilometer altitude since ozone at that height absorbs heat and causes temperatures to become warmer as one goes even higher. This means we get a layer of relatively cold air at approximately 20-kilometer altitude. Also, warm air rises, which means that an aerosol injected at a 20-kilometer altitude will go up and not fall to Earth due to gravity. In other words, it will stay there for a year or two and dramatically reduce planet cooling costs. Way to go, atmosphere! In order to make planet management decisions, we need tools that explain what this is to the public. This would need to be a website since it involves user interaction. Our planet problem can be described with several graphs that show what is expected to happen every year over the next few hundred years. More specifically, these graphs would show expected global temperature increase, sea level rise, food production decrease, planet cooling needed to block tipping points, and amount of money lost due to climate harm. In other words, our planet problem can be described with 5 graphs. And understanding money lost due to climate harm is important since we need to weigh that against the cost of reflecting the sun. Each plot is the sum of multiple components. For example, global temperature increase is the sum of temperature increase from carbon dioxide, temperature increase from melting sea ice, temperature increase from thawing permafrost, etc. In other words, this website could also plot individual components to show what is expected to happen when and where. Before generating these graphs, one would need to select a climate model and several parameters that drive that model. An example climate model is GISS 2020, which was developed by NASA. And an example parameter that drives models is the Earth climate sensitivity. This is the amount of temperature increase that occurs after doubling the concentration of carbon dioxide in atmosphere. Some scientists think it is 3 degrees Celsius, where others think it is 5. This parameter has a big impact on the 5 graphs. Models and parameters are often confusing. Therefore, a planet management website might ask key people for suggestions. And then the website user could specify who they trust. For example, one website user might trust the chair of the IPCC, while another trusts the leader of NOAA. The website user would also need to specify when they expect the world to stop emitting carbon dioxide into the atmosphere. Decarbonizing over 30 to 40 years is desirable. However, many economists believe this will occur later. After selecting a climate scientist and a decarbonization profile, the 5 graphs would then appear. We can do climate change the easy way or the hard way. Our society is currently doing it the hard way. However, for relatively little money, we could do it the easy way. And for even less money, we could help the public explore the easy way with good policymaking tools. For more climate solution videos, visit the link shown here. Thank you for listening.